Then the next speaker will be Professor Karthik Pattabiraman. So Professor Pattabiraman is a professor of electrical and computer engineering at the University of British Columbia. So his research focuses on dependable computer system, cybersecurity, and software engineering. Professor Pattabiraman has received numerous prestigious awards, including the IEE Rising Star Indispensability Award, UBC's Kalman Mentoring and Research Prizes, and the NSERC Discovery Accelerator Supplements. He serves as a vice chair of the IFIP Working Group on Dependable Computing and is a distinguished member of the ACM and the IEE. So now let's welcome Professor Karthik. Yes.
All right, thank you. Thanks for the introduction. It's great to be here today, and I'm very excited because this is my first time visiting Singapore. So, it's beautiful. So, thank you all for coming to my talk. So, I'm going to be talking about security challenges and opportunities in decentralized finance. So, this is work done by my PhD students, Ray Shi and Assem Galeb, as well as together with faculty colleagues Julia Rubin and Zehua Wang at UBC. So, I don't think I need to stand here and convince you that the DeFi ecosystem has been rapidly growing. So if you just look at the last year or two of how much transactions have been transacted, it's in the millions or rather billions of US dollars. So this is great for all of us in this room. Unfortunately, there's also bad news. There's been a lot of money lost due to attacks as well as just misconfigurations and the like in this system. So again, in a single month, for example, close to 700 billion US dollars was lost, and cumulatively, again, the number runs into billions. So this is why it's super important to look at security in the context of DeFi. We can't retrofit it. We need to design it from the ground up. So before I go further, I want to clarify. My background is mostly in dependable computing, of fault tolerance, as well as security. And a few years ago, when we started looking at DeFi, I said, okay, let's see what are some of the dependability challenges. And what struck out to me was that, even well-known techniques that have been adopted in other domains have not been adopted in this domain. And I'll show you some examples of that. So this is an opportunity for us as a community to rethink or think about how to build these systems to be resilient and secure from the ground up. Okay, so I just wanted to also put up this slide to say where we are focusing our efforts. So this is a classic blockchain stack, as most of you probably know from this SOK paper, and there are different layers. So the focus of our work has been primarily on the application layer. We look at price oracle manipulation attacks, as well as the smart contract layer. I know there's another session on smart contract security later today, but some of the work I talk about will also be on smart contracts. So the first line of work I'll talk about is what we've been doing in terms of making smart contracts more secure through static analysis techniques. And then I'll look at more recent work we've done on price oracle manipulation attacks, which is in the larger ecosystem of DeFi. At any point, if there are questions, feel free to interrupt me. You don't have to wait till the end. All right. So I think everybody in this room knows what smart contracts are, so I won't spend much time talking about that. So we're focusing on the smart contract layer. So why do attackers want to attack smart contracts? Well, there are two reasons. One is, of course, they want to make money, so they want financial gain. And they also want to break your service, so it's a denial of service and so on. So the thing, though, is, as you know, these are open to everybody, so it's not a permission blockchain. So anyone who can interact with the blockchain can actually, or has an account on it, can actually mount an attack. So this makes the problem super challenging, right? So there have been numerous instances of these attacks going back from 2016 onwards. And of course, they've all resulted in loss of money. Now, when we started this research around 5 years ago in 2019, we started looking at how effective are existing static analysis tools. So we had an industry partner come to us, and they were keen on choosing a static analysis tool for auditing smart contracts. So we took the state of the art at that time, and we wanted to understand how good are the tools. We also wanted to have a more systematic way to evaluate how we should build these tools. So how good are the current tools doing, and if you build these tools in the future, how should we measure progress? So the approach we tried to do here, and remember, we were not trying to break these tools, we were simply trying to evaluate them. We wanted to go and inject bugs into the source code of the smart contracts, and then run the static analysis tools and say, hey, how many bugs did it find? Seems very simple. Okay, and we injected 3 kinds of bugs. So we looked at injecting code snippets, which are known vulnerabilities. We took existing code, transformed it into insecure code, and we also tried to weaken the security that was already there. Now, you might come back and say, you know, Karthik, this is obvious. Why would a tool not be able to detect this, right? This is like security 101. I'll show you, the risk of giving away the spoiler alert. It's not as simple. Many of these tools were not able to find even simple bugs. Again, we are only injecting bugs that each tool claims to detect. So we are not trying to trick them, and we are playing the role of developers, so a developer who makes a mistake. So here's an example. So this is from Solidity source code. You don't have to read all of it. So what the smart contract has is a bunch of checks that make sure that the message sender is the owner and so on. And one example of a security code transformation we would do is we would remove that check, for example. So now the code is obviously vulnerable, and a good static analysis tool should find this. Now, we could do something even more interesting. We could take existing security, and instead of just removing it, we could weaken it. So for example, we can get rid of the revert here or change it to something else. And again, a static analysis tool should be able to detect this. And finally, we even went and injected code snippets wholesale from other parts of the code. And we made sure these are actually executed as part of smart contracts. So this is not dead code, right? Again, a static analysis tool should be able to detect this. So again, really simple things. Just let's go see which tool or how the tools are doing. And we identified 8 classes of bugs, about 10,000 distinct bugs. So we also tried to make sure the bugs were as distinct as possible. So we built an automated tool to do this kind of transformation and inject them automatically. And we evaluated 6 known static analysis tools. So we can read the names of the tools in a paper. And we measured the false positives and false negatives. So here's the bottom line. And this is where we were surprised. So we had expected that they would detect most of these bugs, and there would be a few that it wouldn't. Honestly, what ended up happening was many of the tools couldn't even detect the simple bugs that we injected. In fact, the highest detection rate was about 50%. And again, these are bugs that the class of bugs the tools claim to detect. If a tool says we won't detect this class of bugs, we don't inject that. Also, even if they detect the bug, often they end up misidentifying the bug. So they say this is a reentrancy attack, but maybe it's an integer overflow. Another interesting result here was that the tools all had high false positives. Again, how we measure false positives is in the paper. But the tools with the highest false positives also have low false negatives. It's a bit like if you cry wolf at every line. You say, hey, there's an attack here, there's an attack here. Chances are some of the time you'll be right? Again, no surprises there. So this result we published, and we released this as benchmarks. Since then, many others have improved on these benchmarks, and there have been better benchmarks since then. And a recent study which replicated this about a year ago, so this was done 5 years ago, but just a year ago, another study replicated it, and they found, unfortunately, the state of static analysis doesn't seem to have improved substantially. So there's been some improvements, but we still have a long way to go. So that's as far as evaluating static analysis tools. Then we started asking ourselves, okay, what is the real reason for these vulnerabilities? If you're a smart contract developer, and I came and told you, don't do this, are you going to follow that, or are you going to say, you know what, these guidelines are just there for the heck of it, I'm not going to follow it. And so we took Ethereum official guidelines, and we started trying to understand how effective are these guidelines. And again, spoiler alert, they're not very effective. So developers seem to even willfully ignore these guidelines. So we did this large-scale study of smart contracts deployed, and both before and after the guideline was deployed. And guess what? We found that developers were actually using the wrong way to, or the insecure pattern, even more so after the guidelines are published. So I don't know why, but it looks like nobody's paying attention to this. So we started saying, all right, so can we do better? Can we do automated replacement of these known insecure patterns? Again, very, very simple stuff, low-hanging fruit. Can we go and try to replace it automatically? And so we built this tool called GoHi. There's a lot of detail about the different patterns we found and so on. But the bottom line is this. It turns out that in more than 80% of the cases where developers, or 95% of the cases, the developers were using these insecure patterns, there was no good reason to do so. So you could replace it pretty simply or straightforwardly with the secure code, and for all intents and purposes, the smart contract behaved as before. So this was a case where, again, it's a low-hanging fruit. You can do this without changing the meaning of the smart contract or inconveniencing developers. And all you have to do is to be able to transform the code. Now, one pushback we got from some developers was they were doing this to save gas. Gas, as you know, is the cost you pay to run your smart contracts in Ethereum. It actually turns out that by doing these transformations, you end up saving gas. So we found, that wasn't the goal of what we were trying to do, but it was actually interesting to us that after transforming, we were actually able to save an average of around 5% of the gas. So again, this is an example where you don't need very sophisticated static analysis, but simple conformance to the guidelines through automated code transformation can go a long way. So that was as far as smart contracts were concerned. In the second part of this talk, I'm going to talk about some recent work we've been doing on the whole DeFi ecosystem and trying to understand the threats and vulnerabilities there. So for this part, again, I'm focusing on the application layer. So this is the stack I showed you earlier. And in the application layer, you're not so much looking at the smart contract, but you're looking at everything in the DeFi ecosystem. So what it's interacting with, what it does, and so on. And it turns out, again, from this paper, that application layer attacks are about 35% of overall attacks. So it's a pretty substantial chunk. And more than, or almost half of this chunk is made up of what are known as these price oracle manipulation, or POMA attacks. So I'll tell you what that is in the next slide. So that's what we decided to target as the first step, right? Because that will give you the best bang for the buck. Okay, so what's a POMA attack? So probably everybody in this room knows what an oracle is. So oracle gives you or a price oracle gives you the price of various cryptocurrencies and how much it is at the moment. So it takes the total liquidity in the pool, divides it by the shares, and gives you the price. And this is usually consumed by the DeFi app, because the DeFi app has no other way of getting the price. And so it trusts what the oracle tells it. Now, it turns out that a malicious attacker can do the following. So you can go, first, let's say you're the attacker, okay, you buy 100 shares from the DeFi app, you pay, say, $100,000. So each one is 1K. Now what you do is, you go and deposit $1 million into the pool, into this this particular cryptocurrency. So now, let's say the original one was 2 million, now it adds 1 million, so it now goes to 1.5K per share. All great, except that now you can go and sell the 100 shares you bought at an inflated price, okay, get a nice profit of 50K USD. And if you did this through a flash loan, you're not even on the hook for the money, because the transaction will not even get committed, and you can do this manipulation as many times as you want with as much money as you want. Now, you might look at this and say, this is a feature, not a bug, right? So the whole idea is that you want these prices to be dynamic, and that is true, but you don't want it to be so easy to manipulate that people start doing this just to make money, because then you're not really creating value. Now, it turns out that this is not as simple as what I showed you. Okay, if it was really as simple as the example I showed you, this would be a no-brainer, and many of these exchanges would have already detected this. The problem is you can do this in very sophisticated ways. So for example, we found that attackers do this not just individually, but with gangs. So they have, say 50 people will gang up, and say 1 or 2 people will manipulate the price. The other 48 will go and do this kind of trading, and they're all in on it, of course, so they know who it is. Could even be the same person. And all of these accounts will coordinatedly try to arbitrage at the same time. And of course, this being the blockchain, you don't know who these people are, but we have their account information. And they can also split it across multiple transactions. So prior work, which tries to detect these attacks, assumes that the same transaction does both the price manipulation and the arbitrage. But attackers are smart. So the moment people try to implement those defenses, they went and said, we'll split this into multiple transactions. And finally, the DeFi protocol itself is evolving, right? So some of the prior work which used fixed patterns doesn't quite work. So you want first principle rules, not just patterns. So here's the sort of the 10,000-foot level view of what we did here. So it turns out we didn't actually have to solve this problem. Because guess what? The US Security Exchange Commissions, and I'm sure Singapore and other countries have similar commissions, already have solved this problem for us. Because this is not a problem unique to DeFi. This happens in traditional stock markets too. It's called market domination or wash trading. And if you do this, the SEC will come after you in the real world and put you behind bars. And so because it has to be defended in a court of law, there are actually very, very, very detailed specifications about what constitutes each of these. So all we had to do was to take those specifications, and of course they're written in English, right, because they're for courts to interpret. We converted them into formal specs. So I'm not going to go into all the details. Here's an example of a spec we did for different kinds of market dominations. And once you have a formal spec, you can build a tool, an automated tool to go and look at all these transactions and figure out whether or not it's a POMA attack. All right, so that's the high-level idea. However, if you try to do this in a naive way on the blockchain, you're going to run out of both space and time because there are tens of thousands of transactions that are happening, and it's almost impossible to keep pace with those. So remember, I told you there's not a single transaction, right? So an attacker can manipulate the price. Their buddies can go, arbitrage it, and then they can manipulate the price. Their buddies can arbitrage it. So this can go on for quite a while. So you really can't go and monitor everything all the time and cross-correlate it. But there are two things that we can leverage here to keep the search process efficient. The first is perhaps obvious. So if you're an attacker, and there's a cryptocurrency or you can make, say, $1 billion profit in one case and $1 million profit in another case, which one are you going to choose? Obviously the 1 billion one, right? So you'll go after the high-value cryptocurrency. And that's enough for us. So we are going to look for manipulations of the high-value cryptocurrencies. That already shrinks the price, shrinks the space. The second thing we can do, it's a little more subtle. Remember, all transactions on the blockchain are public, right? Everybody can see it. So it turns out there are some people who have nothing else to do except to watch these transactions and immediately identify an arbitrage opportunity if one arises. So if you're an attacker and you manipulate the price and you sit on the arbitrage, chances are you lose it because other people will rush it. So you have to time this accurately. So you've got to say, within a very short time of me manipulating the price, I'm going to get the arbitrage. I'm going to tell my buddies to come and cash in on it because otherwise it'll be gone. So we can look at things that are close in time, and that is the two heuristics. So I'm going to quickly show you some of the results we obtained in the space. So we evaluated 3 metrics. So we looked at the number of POMAs detected, the execution time, the false positives, false negatives. So the tool we called is POMA Busters. It's like Gang Buster because they're all doing this in gangs. And we compared with this prior work, DeFi Ranger. And we looked at real transactions on the Ethereum transactions starting from 2021 onwards. But of course, these don't have ground truth labeled. So we also looked at the Code for Arena data sets, which actually have labeled ground truth to measure false negatives. So here's the sort of the high-level result, okay? So the y-axis on the left is the time, execution time. The y-axis on the right is the number of POMAs detected. POMA Buster is our work, DeFi Ranger is the prior work. So the first thing you see, so this is when you run this on the entire Ethereum logs, okay? All the 800 million of them. Now what we find here is that in terms of time, we are faster. So we are getting 20% less time than DeFi Ranger. And the reasons have to do with how we are detecting it because we use first principle rules. They try to learn the patterns, so it's a more complex algorithm. But the real big winner is that we end up detecting 3 times more POMAs than they do. Why is that? Because DeFi Ranger only looks at single transaction POMAs, and they need these patterns to be an exact match. By going back to the first principles and looking at these correlations across transactions and not relying on patterns, we can detect many POMAs that their tool would have missed. And just to make sure we are on the right track here, we also created a version of our tool with just a single transaction, and we were able to find similar results as them. So again, just by changing the game and not looking at patterns, but by looking at first principles, you can detect a lot more of these attacks. Now again, we want false positives, false negatives to be low. So we compared with this, use the Code for Arena data set for the false positives. Again, compared with DeFi Ranger, we had no false positives, they had about 75%. And for, other way around. For false positives, we had no false positives, they had about 21%. For false negatives, again, we had no false negatives, they had about 75%. So again, this shows that if you go back to the first principles, it's very difficult for attackers to evade it, even if they know about your attack. And here's perhaps the most interesting result we found. Okay, the most interesting result was that it turns out this stuff is happening in plain sight. Attackers are not even hiding here. That's how brazen they seem to be. Now, I should qualify this by saying I can't for sure say that everybody who does this is an attacker, because some people could have been innocently leveraging the arbitrage opportunity they saw open up, and good for them, they made a windfall. But chances are that if you're doing this so close to when the price manipulation occurs, you're in on it. You have information. So the total number of operators who are doing this are about 3,500. So it's not too large a number. It's still, we could kick these people out if we want. But here's the interesting thing. They make a profit of about 77 billion USD. Now, this is not all in one person or all at one time. It's over these 2.5 years. But that's a substantial chunk of money. So if you can implement some of these measures and prevent this, you can really save so much money from being transacted. And which is more, like I said, the attackers are not trying to hide their tracks. So 95% of them use their addresses. In fact, I have all the addresses. If you want, come talk to me after the talk, and I can tell you, share the addresses of these people. Of course, I don't know their real-life identities. And even more interestingly, only about 2% of them even bother to use anonymization services. So the rest of them just go trade. You can tell who they are, at least the blockchain address, and they don't care. So this is the state of the DeFi ecosystem. So I'm not trying to say that there's a lot of opportunity here. Maybe things could be better, and there are a lot of low-hanging fruit that we as a community can invest in. Okay, so this is the takeaway here. So I hope for this part of the talk convince you POMAs are an important class of attacks. There have been many, many POMAs in the last 2.5 years valued at $77 billion. And which is more, POMA Buster, our tool, can detect most of these, spans multiple transactions using first principles rule. We're still not able to run this in real time, because real time means you should check not just the transactions that are committed, but all the transactions that are in flight, and that takes more time, but we're getting there. And we also have no false positives or false negatives. So that's the POMA Buster work. So in the next few minutes I have, I want to tell you a little bit about some of the future work that I see in the space as well as opportunities. So the first thing we are looking at is, can we generalize the lessons we learned in building POMA Buster? So one of the challenges is, if you want to go build these things to go look for anomalous patterns and so on, there's a lot of engineering effort involved. So we want to be able to abstract this, and ideally, we want to support patterns that we haven't seen before. So what we're trying to do is, so there's this work that looks at uncovering attacks from transactions, and we are trying to build on that, and instead of just looking at opcode patterns, we are trying to look at the entire call tree. So can we construct the dynamic call tree just from the transactions? And spoiler alert, we are trying to see if LLMs can be used in this process. Okay, again, one more potential application of large language models. And we're also trying to look for unusual sequences of these transactions. Again, LLMs are very good at this because they have this autocomplete-like model. But of course, as everybody knows, LLMs can also hallucinate, so that's the challenge. And we're also trying to look for outliers, maybe use invariants and so on to detect some of these. And even more, perhaps, broader issue we're looking at is DAOs. Here, we have these proposals that are submitted and code, and you need these to be approved by the majority of users for DAO contracts. It turns out that there are some people who willfully deceive by submitting a different description from the code, and there's been prior work that's looked at that. But what we want to do is go beyond just deception. So maybe sometimes you submit a contract, you're not trying to deceive, but that is actually, or a DAO, but that's actually the wrong proposal. So that has downstream implications. So can we find out not only that someone is being malicious, but they're being naive? Like in the Solidify example I gave you, developers are doing their best, but even then the static analysis is not helping. So can we do better? Okay, so this is something we are trying to work on. So to conclude, this is my last slide. I hope I've convinced you that DeFi security is important. So we started with smart contracts, and we moved to the DeFi ecosystem. But I think the problems that we are finding, and many others in the Zoom are finding, will endure for many years. So we have to be able to solve them, not just in a way that appeals to us researchers, but actually takes it to the practitioners. Because as we are seeing, practitioners either don't care or they don't really follow these guidelines. So I presented a couple of future directions on anomaly detection and preventing governance attacks. And we're actively working on these. So if there are any questions, I'm happy to take them. Thank you very much.
I think we have time for 1 or 2 questions.
Sure. Yeah.
So let's start with other way. Thanks so much for the nice talk.
Thank you.
Really enjoyed it. I have 2 questions. Maybe one is a comment. Is there a reason that in the smart contract security you focused on static analysis tools? I think
on what?
On static tools, because I mean in security at least it's quite well known that they have lots of limitations. And I think kind of the direction nowadays is to go for dynamic analysis, fuzzing, symbolic execution, whatever it is, or a combination. So that's the first question.
So the answer is for that study, we only focus on static analysis tools because we were doing the code transformations into the smart contract code itself, right? But actually, since our work, others have also done this for dynamic analysis tools. And the results aren't that promising, unfortunately. So
I believe fuzzers will handle these cases that you showed today very well.
Right. So for sure, you can detect this. I'm not saying there are no tools that detect them. There's no one tool to rule them all, right? There are different tools that detect different parts of it. But I want to say for the second part of the talk, the POMA Buster work, that is purely dynamic because we are doing this based on the transactions. So in fact, once you go to the DeFi model, static analysis, pure static analysis won't cut it anymore because there are all these interacting entities. So you need dynamic analysis there.
Right. And that takes me to the second question.
Okay.
I like the analogy in your SP paper on how does this tie to existing models in the US, whatever, but I couldn't understand the relationship in the sense that in the current fiat world, people have identities and you know their address and you just fetch them. Here it's pseudonymous and it's very easy to catch, but it's also super easy to elude. Now, in my view, it's game theory. People are not changing their address because they're not being detected.
Right.
They start detecting, they start changing their address. So what? So what is the outcome here? That's the question.
Great question. So maybe I should clarify a couple of things. So we are not relying on knowing the addresses to do the detection. So we're looking at whether or not there is this cycle where somebody tries to manipulate the price and others rush in to do the arbitrage, right? So even if they hide the addresses, our tool would still be able to detect them. But you're right. Today the state of the art is such that there's very little consequence for getting detected, or even just getting detected, that attackers don't bother, right? So part of what I want to maybe raise awareness here is there is a lot we can do as a community to try to get even low-hanging fruit adopted. So if all the coin exchanges, all the exes said, we are going to deploy something like POMA Buster to detect these things, and we'll kick out the people who trade, right? So that raises the barrier. Now, sure, there'll be some people who will get under it, maybe they'll hide their tracks well, but this is where I think we should start going, right? We're not there yet.
Makes a lot of sense. Thank you so much. Thanks.
Thank you. Any other questions? Oh, sorry.
Yeah, hi, Professor. I'm a scientist in A-Star Singapore, so I'm quite interested in the last one, the government attack in DAO. So I just wondering, what kind of a government attack you are talking about in DAO, and what kind of solution you are proposing to address
So it's work in progress, so I don't have a solution, but I'll tell you what kind of attacks we're talking about.
Yeah, I know. Okay.
So the attacks we're talking about are where someone, the person submits a proposal along with code, right? And typically, it's easy to catch out people who are downright malicious, right? If their proposal says something completely different from the code, then today you can examine it, or there are tools that will help you and you can find that. But what if it's more subtle? What if there's some corner case in which the code doesn't match the proposal that they're submitting? So it's easy for a user to look at it and say, this looks okay. Or even more importantly, what if there is a bug in the code, right? Maybe the person had good intentions, But as you know, the road is paved with good intentions. So we want to make sure we can provide guarantees to the people who are voting on this that the proposal actually matches the code.
So it's more from a code level, right? It's not from the logic level.
That's true, yeah. But code together with the proposal. So we're trying to use LLMs to analyze the proposal because that's natural language, and then correlate it with the code. Oh. Yeah, but we haven't solved the problem, right? So that's still an open problem.
Thank you. Thank you.
Okay. Thank you. Okay, thank you, everyone.